Okay, nobody asked me any questions about the homework, so I'm trusting that things got done this time. And we're going to talk about transient circuits. So transient circuits, we talked about them in class yesterday, and I said, today, we're going to do the calculus. So here's your basic transient circuit. You've got a battery, you got that switch. Now notice this one here is different than what I showed in class. It's different because it's a simpler design. It's charging and discharging through the same resistor. That way you don't have two time constants. So what I showed in class had two time constants, a charging time constant and a discharging time constant, which is a much more standard problem. But for our analysis, this is the simplest circuit. So it can be used in a charging or a discharging situation. Things to do before we get started with trying to solve how this works. Number one is recognizing the relationship between capacitance, charge, and voltage gives us a relationship between current and voltage. The relationship Q equals VC, or capacitance is defined as the charge separation divided by the voltage difference. I'm using lowercase here instead of uppercase for Q and V because they're going to be things that I'm going to vary in time today. And so Q equals VC, and then we just take this and we take the derivative of both sides. So dQ equals dCV. And we're going to go ahead and do them both with respect to time. I didn't give myself enough space. We're going to do them both with respect to time. So but since capacitance is constant, that gives us simply dQ dt is equal to C dV dt. And so that's a fundamental relationship between the rate at which charge flows to the capacitor and the rate at which the voltage on the capacitor changes. But of course, dQ dt is our definition of current. And so this equation is written down below as current is equal to C, dV dt. Now that actually has an important ramification. You have, well, what's the maximum current you can achieve in theory? Infinite. In theory, the rate you transfer charge is infinite. In practice, you know it's not going to be infinite. And so if the current is finite, then that tells you dV dt, the rate at which voltage is changing on your capacitor, is also finite. So you can't have a discontinuous change in voltage on a capacitor. The capacitor cannot go from 0 volts to 10 volts when you flip the switch. It's going to take some time. And you might propose, I could come up with a circuit that violates that, oh great wizard. I can make a circuit that has a battery and has a capacitor and has a switch. And if I close that switch, am I not going to have an instantaneous jump from 0 volts across the capacitor to whatever the EMF of the battery is?
It seems like it should, but it doesn't.
It seems like it should, but then we have to face the realities. That wire does not have zero resistance. It has a very low resistance, but not zero. And so we're going to have a time constant based on the wire, even if it was, now I put a battery, the battery's going to have an internal resistance as well. But we might have a, ideal voltage source. Even if we had an ideal voltage source, you have the resistance in the wire. So it's still not going to jump instantly. It's going to be very, very quick, but not instantly.
What about superconductors? Do they still technically have resistance?
Yes, they have resistances that are about 1/billionth the resistance in a normal wire. So normal wire, for this class, we treat as no resistance. It's 1/billionth of that in the superconductor. And so then for any class, you treat that as essentially no resistance. So this is going to be our primary equation to do the calculus to calculate the charging of our capacitor. So we have our circuit, same pictures I drew before, and we can do it in charging or discharging. I will just ask you, which one do you want to do first? Charging case or the discharging case?
Charging, because that no one comes first.
Okay, so Alex says the charging case. So in that case, we're going to be going from a circuit with no connection to a circuit that has this. And I'll have current like that, resistor here, capacitor here, and I'm going to put E for EMF there. I know it said VB and VC, but I'm just going to put EMF for the voltage, the power supply. So let's look at this circuit, the one that I've written in blue, and let's find a relationship between voltage and current for this circuit. Now, the first thing we want to do, just like we'll do in the lab today, just like you've been doing on the homeworks, is say, okay, the current is going through which side is positive for the resistor? So will it be the left side or the right side that's the positive side of the resistor? Said left? You are correct. The side that the current goes in is the positive. The side that it comes out is the negative. Now for a capacitor, we haven't talked about a rule for the capacitor. But we're going to use the same. So if my current's going like that, then it's going to be positive and negative like that. So we have to define which side is going to be positive, which side is going to be negative. Now we go through, since this is one loop with no essential nodes, using Kirchhoff's laws, which one's really available to us? There's no essential nodes. Yeah, you got to use the loop if you have no essential nodes. And so we're going to use the loop law. Sum of the voltages on the loop equals 0. And so I'll just start here. Am I going up or down through that power supply? Up. Okay. So I'm going to have plus my EMF. Through the resistor, am I going up or down? And I'm going to put for now V sub R. And then going through the capacitor, am I going up or down? Down. So there's my equation. Now that's not the variables I want, but I have it just written out in regular old voltage variables. Now we'll make the substitution. V sub R is equal to IR. And we know that, that this relationship is going to apply, that the current that is flowing through that circuit has to be the same in everything because it's one loop. It's C dV dt, where dV was the derivative of the voltage across the capacitor. So since the current through the capacitor is that, it has to be the current everywhere. So I'm going to substitute that in and have equals C dV capacitor dt times the resistance. So now if we look at this equation, substituting V sub R, we have that. Now, in solving an equation like this, what we normally do is we will put the derivative on one side just by itself. So I'm going to divide everything by RC and put everything else on the other side of the equation. So I'm going to rearrange this equation. So I have, so this equation here becomes, move this across so it's positive, dVc dt, and right now I'll still leave it with the RC. And then divide everything by RC. So I have and keep in mind my C's may be a little sloppy, but the only voltage here is the voltage across the capacitor. Now we're to something that you guys have done in this class. It is differential equations, but we had to do it the first week of first semester of this class. How do I solve this equation for the voltage across the capacitor? What's the first step from this point? I need to separate the variables. So what are the two variables? Okay, V and T. And I need to have the D's on top. So I'm going to have to take this, and effectively, you guys are astute enough on math to know that I can swap those two, right? I multiply both sides by dt, divide both sides by E minus VC. And I have the equation that says that. Now we have the left side is only a function of VC. The right side is only a function of time. And so I can integrate the two sides separately. So I integrate the two sides separately. And it's going to be from V initial to V final. And from T initial equals 0, because why would you set your starting time anything besides 0? To T final. Okay, so now we have to do the left side of the integral here. What's the easiest way that you can think of to do the left side of the integral?
Substitution.
Yeah, I do a U substitution. Is that what you were saying, Alex? Good. So we'll use a U substitution. So there's the two substitutions. And I will have my new integral from E minus V initial to E, that's a nice E, minus V final of my du becomes minus, or my dVc becomes minus du over U. Well, that's just going to be minus natural log of so there I've done the left side integral. The right side integral is pretty trivial. What's the right side integral? Minus 0. So I have an equation here. I've done the two integrals down below. There. And so my equation is now minus natural log EMF minus voltage final over EMF minus voltage initial equals T final over RC. Well, we've got that pesky minus sign. What's the quick way to get rid of the minus sign? Okay, the quick, legitimate way. Help me out, Corso. Well, we can just multiply both sides by -1. I got rid of the pesky minus sign on the left side. Ignoring is what I did in the first couple of lectures this semester when I made some sign errors. I said, I know I'm wrong. I'm not going to worry about it. Here, I'm going to make sure I'm right because it would make a big difference. Now I have a natural log. How do I get rid of the natural log? E. So E raised to all of this stuff is equal to E raised to all of this stuff. So that gives me the equation Now, at this point, I'm going to make my simple substitutions going back to let V final just become the voltage across the capacitor at whatever my final time is. And T final will just become T. And then our definition that tau is equal to RC. So using those substitutions, my equation is that, let's cross, we want to solve this for voltage across the capacitor. So multiply both sides by E minus V0. E is EMF, of course. So on the left side, I cancel it out. And I have so now I'm almost done. Almost done. I need to solve for VC. So I'm going to subtract my EMF from both sides. And then I have to multiply by -1 again. And I have, so I subtracted E, so it becomes a positive. I'm actually going to leave it at the end. Because I'm multiplying by -1 in this parenthesis, I'm going to have there's the equation for the voltage across the capacitor while it is charging. Now we have to go through this and say, while it is charging, what was the initial voltage on the capacitor before I started charging? It was 0. What was the rule about the instant I flip the switch, how does the voltage change? Okay, it's going to start to increase, but it has to be continuous, so it can't instantly jump.
So the instant 0 still.
So it's going to be 0 the instant I start, because that's where it was before I started. So in this problem, for this specific derivation, the V0 would be 0. And so I'm going to write this down because it's a specific case. So that's what we found for this specific case. That's the equation that we had in class yesterday that was just given on faith. That the voltage is EMF times 1 minus E to the minus T over tau. It starts with a voltage of 0, and then it's going to build up. Notice the E to the minus T over tau, when time is 0, that's 1. So I have the EMF times 0 at time equals 0. And then that second term is asymptotically approaching 0. So that means that my voltage is asymptotically going to be approaching the EMF. But this is not the one I put the box around. I put the box around this equation because this is the one that's generally true. You don't have to start with a capacitor that's discharged. I could go back to my circuit and I could have started with it on the charger, then moved it to discharge, and then when it's halfway discharged, I could have moved it back. In that case, my V0 would not be 0. It'd be whatever the voltage on the capacitor was at the moment I switched it back. And so the equation that's in the green box here is the generally true one. And what we do is we say, well, the V0, that's the voltage it has when you start. The EMF here is going to be the peak voltage, the voltage it gets after an infinite amount of time. And so the equation that I teach my students when I teach circuits is I say that EMF is the voltage it's going to have after an infinite amount of time. Because your circuit could have something other than just a battery there. You could have something that's a complicated circuit connected to it, and the voltage is, something else entirely. But if you figure out what the voltage of the circuit would be, the V0 is the voltage the circuit would reach in normal situations after a long time in the initial condition, unless you're given something specific. The V infinity is definitely going to be the voltage you would have after infinite time in the new position of the switch. You determine those two voltages, and then you have all the voltages to put into the equation. Now we have that tau that also is a little more sophisticated. In class yesterday, we had just a resistor and a capacitor. But what if we have multiple resistors? What are you going to use for R then? You have to combine them using our rules for series and parallel resistors. What if instead of one resistor, you have one problem that has two resistors in series, or capacitors. You have two capacitors in series. What do you do if you have two capacitors in series? You're going to have to combine those. That's correct.
Oh, so you'll just treat them as one, but you had to choose to get the new capacitance?
Yes, that's right. So this is the equation for charging. Or it turns out for discharging, right? Because now that we have it in the V0 and the V infinite form, we don't have to go back and do the other problem because we just say, well, what was the voltage before we started and what would the voltage be after an infinite amount of time? And this equation is still going to work.
So we would have gotten this equation if we decided to start it.
Well, we would have gotten it without the EMF. And so we would have had just one term instead of three terms, right? Because we technically have three terms that I factored. And so we would have had to come back and do it again if you had made the other decision. You say just time. Yeah. But it's a quicker derivation the other way because you don't have as many items to worry about, right? There's no reason to do a U substitution if you didn't have the EMF in there. So it's a quicker derivation, but you have to come back and do this one anyway. So that's the equation for the voltage when you're charging or discharging the capacitor. Now that we have the voltage equation, how do I find the current?
We have a relationship for them.
Or maybe current is C dV dt. All I have to do is take the derivative and I'll have my current. Uh-oh, went too far. Nope, didn't go down low enough. That's what I did. So I is equal to C dV dt. So I just take the derivative of that. What's the derivative of e to the minus t over tau? Well, it's not just the same. It's going to end the same.
Negative t over tau times e to the negative t over tau.
You bring down the derivative of the exponent.
Oh, right, t.
So minus 1 over tau. And then, as Corso said, the same, e to the minus t over tau. And what's the derivative of a constant? It's 0, so I'm done. Now, tau is RC. So we'll cancel out those C's. And so it should be like that. So we're able to, once again, we found the voltage and current.
Wait, the negative.
Where did the negative? Okay, this was minus 1 over tau.
Oh, and tau is negative RC.
And so tau is,
RC.
well, tau is RC. The minus is from that minus 1 over tau. And so that's going to tell me the current flowing through my capacitor at any time. And of course, the voltage initial here was 0. The voltage final was, whatever my EMF was, minus 0 minus negative makes it positive. We would have a positive current for this case. And, well, there you have it. So, general rules. Now that we've done everything, general rules, you can use these two equations with the definition of RC. The voltage is going to be the starting voltage minus the infinite voltage, in parentheses, e to the minus t over tau plus the infinite voltage. The current is going to be starting current minus the infinite current, e to the minus t over tau plus the infinite current. They both have the same fundamental form. What should the infinite current be for a capacitor? Always. After you wait an infinite amount of time, what's the current going to be for a capacitor circuit?
If it's charging,
In any circuit, it's going to be 0 because it's going to reach its final charged state or discharged state, at which point there's no current flow. So the I infinity is always going to be 0. And you might say, why are you showing me this stupid equation if the I infinity is always 0? Doesn't that make, it's a reasonable question. The reason is, in a couple weeks, we're going to be studying inductors. And we'll do the same type of calculation, and we're going to find exactly the same two equations. But for the inductor, I infinity is not 0. And so I put it in this form so we have exactly the same equation for an inductor as we have for a capacitor. The only thing that's going to be different is the definition of tau. The time constant for an inductor is something different than inductor resistor current circuit. So that was my goal for today, was to derive how the RC circuits, transient RC circuits. Transient means it's changing from one state to another. So it's not steady state. It's not AC. It's changing between one steady state and another steady state. So any questions about what we've done today? What was the fundamental relationship that I have to have if I'm going to do this derivation?
current equals capacitance dV.
And that simply came from the definition of capacitance. But that was the starting point. Without that, none of this derivation is possible. We have to have the understanding of how charge and voltage relate in a capacitor.
But isn't capacitance also just kind of like a made up? I think it's really hard to just measure. I mean, it's not really hard to measure it, but isn't it basically just a relationship between charge and voltage? Like,
It's defined as the relationship between charge
right.
and
So it's
voltage.
not like speed where it's really obvious that it exists. This one you had to come up with as a relationship.
Well, going through theory, remember when we talked about like the parallel plate capacitor? In the parallel plate capacitor, you can show that based on your physical construction, there is going to be a fixed relationship between charge and voltage
So that's
until you get to too high of a voltage when you have an arc go through, and then it destroys everything. Right, so in the operating range for voltages on the capacitor or charge on the capacitor, that relationship is going to hold true. Now, easy to show for the parallel plate. If it's some other geometry, it's going to be much more complicated to show, but you're still going to have a linear relationship between the two if you don't have arcing.
So finding the capacitance would be difficult, but capacitance
Well,
is still gonna
finding the theoretical capacitance would be difficult in some bizarre arrangement.
right. But
But
it would
measuring
still
it
end
still.
up being charge over voltage.
Yes, because that's how it's defined. And so our equation of epsilon aught times area divided by separation is only for a parallel plate capacitor. Right? For other things, it's going to be more complicated because your geometry is not so simple. But you're still going to have a linear relationship. Okay, so could you do this derivation on your own?
The one you said.
I think I could give it an hour. Just to have extra time to play with. But yeah.
Because that's the kind of thing that you should be able to do. You should be able to start with, here's a capacitor in a circuit, show using calculus, not an equation that's given, how the voltage on the capacitor is going to change in time.
Well, this one was easier than any of the stuff we had to do in the homework. I mean, not only just because we had derivatives instead of integrals, but because there's no spatial component.
Mhm.
Because, like, I have not learned how to integrate with spherical coordinates. Everything I'm doing in this class is completely learned in this class, basically, because
Which is why I spend time on this is what DV is.
yeah, it's just super confusing because
Now you can
I think we've done series and sequences a lot, so that's super helpful right now.
series sequencing.
You know, like Taylor series and stuff. Yeah, basically the same thing we're doing. No, but this is fine because the spatial components are part I have trouble with integrals. And since this doesn't have that, it's
Now with the homework, you can do all of those problems as single integrals, as you do a shell of area 4 pi r squared, and then you just integrate dr.
yeah.
Right. In our integrals, we always had the two that were simple that came out to be 4 pi, and then we were integrating r squared dr for the last one, and whatever our function of r was. So they all came out to be effectively single integrals.
Yeah.
Okay, so I'm done with class. If you want to ask me questions, I said I extended the time for the homework because I didn't have it set to 11:30 like it was supposed to be, and if it's not set to the right time, you really can't turn it in now, can
I guess.
you? What about you, Corso?
Hmm?
What about you? Any questions?